Okay, hello everyone. Welcome to the 116th online Spintronics seminar. It's been a while since we met last time. I hope all of you have doing fine. It's my great pleasure to introduce our speaker today. Dr. Emilie is Associate of the National Institute of Standards and Technology and a Senior Research Associate at the University of Colorado Boulder. She obtained her PhD from the University of Grenoble with Spintronics in 2013, after which she did a postdoc at NIST Boulder. Her current research focuses on spintronic devices for neuromorphic applications at hardware level. She's a senior member of IEEE and is currently the chair of the IEEE Magnetics Rocky Mountain chapter. So without further ado, Emilie, please go ahead with your talk.
Awesome. Thank you, Jean. Well, really appreciate being here and having the opportunity to talk. So thank you for inviting me. Today, we're going to talk about a device that we developed at NIST, which is a nanoclustered magnetic Josephson junction. And we're going to discuss how we can integrate this device in neuromorphic computing. So before I start, I'd like to acknowledge all the people who contributed to this work from different institutions. I'd like to point out that the idea of the device that I'm going to talk about here has been proposed by Stephen Hosek. And some of the results that I'm going to present have been obtained by Mike Schneider, who originally started this work. So here is the outline of my presentation. So I'm going to start with an introduction, and we're going to present our motivation to study neuromorphic computing. And sorry, in the second part, we are going to introduce the device, which is a nanoclustered magnetic Josephson junction. And I'm going to show that we can use this device as artificial synapses. And finally, I'm going to show how we can integrate this device in a neural network for neuromorphic applications. Okay, so let's start with this introduction. So basically, the principle of a bio-inspired neural network consists in building a network of neurons that are connected by synapses. So here, the role of the synapse is to adjust the strength of the connection between the neurons. So typically in our brain, the synapses are responsible for the plasticity, which is this capability that we have to learn and to modify our memory. So in a simple picture, so in a neural network, you have an electrical spike that is emitted by a presynaptic neuron. This spike is then transferred to synapses, which is going to modify the amplitude of the incoming signal by applying a synaptic weight on the signal. The spike is then transferred to a postsynaptic neuron, which is going to sum all the incoming signal, and it's going to decide, based on this sum, if it's going to trigger a spike in output or not. So all these actions can be simulated at the software level through algorithms. And so it turned out that the bio-inspired algorithm has shown increasing performances over the last decade, and it allowed many excited applications that we use every day. But all these applications are all done at the software level. And for that, to obtain this high computational performance, we also need to have a significant domain in terms of training. So on this graph, I am showing the amount of compute that you need to train a single model as a function of the years from 1960 to today. What we can see is that since 2012, the training demand has been doubling every 3 months. So just to put that in perspective, this is about 7 times faster than what we typically observe with the Moore's law. So you can imagine that this high training demand of these software algorithms has a cost in terms of time and also in terms of energy. So one solution that has been proposed to reduce this cost is to invest research in neuromorphic computing. So basically, neuromorphic computing is hardware for AI at the device level. And we want to invest in neuromorphic computing because it has the potential for fast and low energy computing. So to make hardware for AI at the device level, we need to be able to recreate all the building blocks of a neural networks at the device level. And typically, that would include the neurons as a signal source for the presynaptic neuron or as a signal analysis for the postsynaptic neuron. It will include the axon, which is this channel between the neurons that allows this signal propagation. And it will include the synapse, which allows to apply a weight on the signal. So it turns out that all the building blocks that I describe here, the neuron, the axon, and the synapses, can be realized with a superconducting device that is a Josephson junction. So don't worry if you don't know or don't remember what a Josephson junction is. I'm going to make sure to remind the properties that you need to know. So why are we interested by the Josephson junction? So it turns out that the Josephson junction is naturally a very good candidate for neuromorphic computing. Indeed, in the same way as we can transfer information in our brain by emitting quantized pulses, the Josephson junction naturally emits quantized pulses that are called single flux quantum. Additionally, so in the brain neural network, we have these axons that allow to propagate the signal. We can also do that in Josephson junction with Josephson junction by using transmission lines that allow us to propagate the signal on very long distance without any loss. I also mentioned that the plasticity is obtained through the synapses in the brain. And in this presentation, I'm going to show that we can reproduce the synaptic role by using a magnetic Josephson junction. So this is going to be the focus of my talk. And finally, the Josephson junction is also a very fast device that can spike 1 million times faster than the brain. So as you can see on these figures with the 2 different time scales. Okay, so here we start getting an idea about why the Josephson junction can be interesting for neuromorphic computing. So with that, I'd like to move to the second part of my talk, where I'm going to describe the nanoclustered magnetic Josephson junction. I'm going to show how we could use it as an artificial synapse. So before we dive into the magnetic aspect of the device, let me tell you a few basic properties that we need to know about a Josephson junction. So a Josephson junction is a device that consists in 2 superconducting layers separated by a non-superconducting barrier. This device is typically characterized by its IV curve, which is a curve that describes the voltage measured through the device as a function of the current applied through the device. So we're going to see several of these curves in this presentation. So I wanted to take a moment to explain them. So an IV curve has typically 2 different regimes. The first one is a regime that we observe below a critical value that is called the critical current, and in which the Josephson junction operates in a superconducting state. Above the critical current, the device will emit some quantized spikes that are called single flux quantum. And in this regime, the DC voltage that we measure is a time average value of the spiking state of the device. So here it is a lot of information. And really the only thing I want you to remember is that the main parameters that characterize the Josephson junction is its critical current. And we can see the critical current on this type of curve by the boundary between the 2 regimes. Okay, so the Josephson junction that we are going to study here is special because it is a nanoclustered magnetic Josephson junction. So what I mean by that is that in this case, we have magnetic nanoclusters inside the non-superconducting barrier. So I'd like to mention that for a long time, people were really reluctant to use magnetic materials close to superconducting devices because the magnetism tends to kill the superconducting effect. However, if we use it well, this combination can bring interesting properties. For example, here, we're going to see that we can combine the natural spiking behavior of the Josephson junction with the plasticity from the magnetic clusters to obtain some synaptic properties. Okay, so let's have a closer look at our material. So the device that we study has a barrier that consists of nanoclusters of manganese inside a matrix of silicium. This barrier is enclosed between two layers of niobium, which is a superconducting material. So this material is deposited with sputter deposition. And to obtain the magnetic nanoclusters, we deposit some multi-layers of silicon and manganese to obtain, and we anneal it at 400 degrees Celsius to create the formation, to allow the formation of the clusters. So once we have this sample, we can pattern it with optical lithography into the shape of a pillar between 1 and 10 micrometers. So here is pretty big devices compared to what we can use in Spintronics in general. Okay, so we study the magnetic properties of our device by using squid magnetometry. So here we see the magnetic moment as a function of the temperature between 4 Kelvin and room temperature. And what we see is that the temperature that corresponds to the maximum magnetic moment is called the blocking temperature. Above this temperature, the nanoclusters are in a superparamagnetic state, which means that the magnetization of the nanoclusters is unstable due to the high thermal energy. When we get below the blocking temperature, the magnetization of the nanocluster is blocked in a fixed orientation. And we can actually use this property to influence the orientation of the nanoclusters. So for that, we will heat the sample above the blocking temperature, and we then cool it down in the presence of a magnetic field in the direction where we want to orient the clusters. So we repeat these measurements in presence of a magnetic field. And in this case, we observe that the magnetic moment at low temperature increases with the value of the magnetic field. So here, this means that we are ordering the magnetic clusters. So basically what that means is that in this example where we have the lowest magnetic moment in absence of magnetic field, we have a device that is magnetically disordered, meaning that the magnetization of the clusters are all pointing in random direction. However, when the magnetic moment is maximum, we have a device that is which has a highly ordered magnetic state, meaning that the orientation of the cluster magnetization are aligned in the same direction. Okay, so here really the takeaway of this slide is that we can control the magnetic order of the device with the temperature. Okay, so to measure the device electrically, we place the sample inside a probe station that we operate at 4 Kelvin. And we use two GSG probes, so ground signal ground probes, one to apply a current through the device, and the other one to measure the DC voltage through the device. So once we have that, we can measure the IV curve of the device in two different configurations, when the device is magnetically disordered or when the device is magnetically ordered. what we can see here is that by changing the order of the device, we can modify the critical current. Here, indeed, we see that the disordered state has a critical current that is 2 orders of magnitude higher than with the ordered state. So here it's important to understand that the critical currents can be tuned with the magnetic order of the device. So to control the magnetic order of the device, another method that we use is to apply fast electrical pulses through the device in the presence or in the absence of a magnetic field, which allows us to obtain an ordered or disordered magnetic state. So here I show that we measure the critical current of the device as a function of the number of pulses that we apply through it in the presence of a small magnetic field. We can see that by applying the pulses, we can tune the critical currents, basically by tuning the magnetic order with the electrical pulses. Interestingly, we see that we don't obtain only a low and high value of critical current, as I showed before, but now we observe also some intermediate values of critical current that give us this quasi-continuous variation of the critical current with the magnetic order. So this result is very important here because it is this property that's going to allow us to use the critical current as a synaptic weighting. So before I move further, I'd like to point out that we don't understand all the physics behind this device. And for example, we don't understand why we are able to reorient the clusters with electrical pulses. One hypothesis that was made is that we are heating the device when we apply the pulses through it. However, even if we consider that the entirety of the pulse energy was transferred to heating, this difference of temperature will not be large enough to explain the reorientation of the device, of the magnetic cluster, since it is way below the blocking temperature. So here, just wanted to point out that there is a mechanism that we don't understand well, and I'm going to mention it again in a few slides. Okay, so I told you earlier that hardware for AI at the device level has a potential for low energy computing. So I think that we should look at the energy of this device. So here I'm looking at the training energy, which is the pulse energy that we need to reorient the magnetic clusters. And this pulse energy is directly related to the magnetic anisotropy of the clusters. We're also going to look at the spiking energy, which is energy that we need to emit a single flux quantum pulse. So here we look at the energy as a function of the size of the device, and we see that this energy is scalable with the size of the device. Interestingly, we see that we can reach some very low values, where for our smallest sample, which is 1 micrometer of diameter wide, we obtain a training energy which is as low as 1 attojoule, and a spiking energy that is as low as 10 zeptojoule. So here we're really speaking about very small numbers. To put that in perspective, in comparison, the brain needs about 10 femtojoule to emit a spike. So we also need to consider the effective cooling overhead that we need to maintain our sample at 4 Kelvin. But even if we consider that, we see that for a smaller device, the energy that we need for this sample is still smaller than the energy needed for the human brain. Okay, so until now, I show some results that are pretty promising for the nanoclustered magnetic Josephson junction. However, there are several points that we don't understand or that we would like to optimize. So for example, I mentioned earlier that we don't understand the transport properties that allow us to reorient the magnetic clusters with the electrical spike, with the electrical pulses. So that's one thing that we would like to study. And additionally, there are several things that we would like to study related to the cluster properties. For example, we'd like to know if there is a relation between the number of accessible states of critical current versus the number of clusters available in the barrier. Finally, I mentioned earlier that the training energy is related to the magnetic anisotropy of the nanoclusters. So here we would like to see, we think that we should be able to improve the training energy if we can optimize the cluster properties. So for all these reasons, here we would like to tune the cluster properties to understand the physics of this device and to optimize its properties. Unfortunately, it turns out that the silicon manganese is not the ideal material system for nanoclusters optimization. So we want to work with a different material system. So for that, we work with the Karlsruhe Institute of Technology, who owns a custom deposition system, which allows to have a very fine tuning of cluster properties. So together, we chose to work with a new material, which is here a nanoclustered magnetic Josephson junction with a barrier that includes clusters of iron inside a matrix of silicon, and with this barrier in sandwich between two layers of niobium. So the sample is deposited with a custom size selective low energy nanoparticle deposition system, and we can choose the properties of the device that here we choose to be the following. So I like to highlight the fact that before this study, we were able to see the synaptic properties of the nanoclustered magnetic Josephson junction on it's been observed on a single material system, which was a silicon manganese barrier. And our first goal here is simply to demonstrate that we can obtain the synaptic behavior in a new material system, which is here the germanium iron barrier. So to demonstrate that we can use this device as a synapse, we need to demonstrate that the critical current depends on the magnetic order, and that we have this quasi-continuous variation of the critical current with electrical pulses. To demonstrate that, we repeated the same experiment that I showed before, but with this new material. And for that, we measure the IV curves of the device when it is in an ordered magnetic state or in a disordered magnetic state. And here again, we were able to observe 2 orders of magnitude of difference between the critical current. So that fulfills this first requirement, where we can conclude that the critical current depends on the magnetic order. Additionally, we measure the critical current as a function of the number of pulses applied to the device. And here again, we observe that we have this quasi-continuous variation of the critical current with electrical pulses. So because we have these 2 conditions fulfilled, we can conclude that this new material system of germanium iron for nanoclustered magnetic Josephson junction can be used as synaptic device. So we're happy about these results, first because we demonstrated that it can be observed on different material system, but also because it opened new options to study the physics of the device and to optimize the materials by tuning the cluster properties. Okay, so this was that concludes the part on the device properties. So now I want to show how we can include this device within a neural network for neuromorphic applications. So for that, we need to build a basic neuromorphic cell, which includes synapses and neurons. And we do that by building circuits that include some normal Josephson junction, which means with a fixed critical current, and some nanoclustered magnetic Josephson junction with a variable critical current. So here the variability of the device is indicated by this little arrow. So this cell contains two parts. The first one is a synapse that includes a nanoclustered magnetic Josephson junction. And the second one is a squid loop that is used as a neuron. So before I describe how this cell works, I first need to describe an important property of the Josephson junction. So in a small signal and linear model, a Josephson junction can be modeled by a resistor in parallel with an inductor that has an inductance inversely proportional with the critical current. So we can use this property to build our synapse by building an inductance divider. So that is simply done by adding a fixed inductor in parallel with the Josephson junction. By doing that, when we apply a current through the device, the current is divided between the Josephson junction and the fixed inductor. Here we use a current flowing through the fixed inductor as an output of the synaptic signal. So it's important to understand that in this case, the synaptic weight is controlled with the critical current value. Indeed, if we modify the critical current, we're going to modify the value of the equivalent inductor. And as a consequence, we're going to modify the amount of current flowing through the Josephson junction and through the fixed inductor. Okay, so to read the output of the synaptic circuit, we mutually couple this circuit with a squid loop, which is used as a postsynaptic neuron. So here you see that when we vary the critical current, which is our weight here, we're going to modify the amount of current flowing through the fixed inductor. This one is coupled with the squid loop, which means that we modify the amount of current flowing through this squid loop. And the current flowing through this squid loop is going to give us our output. So the advantage of this system, this neuromorphic cell, is that it can be extended to integrate multiple synapses. So before we study the case of the extended neuromorphic cell, let's focus on a simple one with a single synapse, where here we want to study the performance of our neuromorphic cell by doing some simulations. So we perform simulation with WR-SPICE, which give us circuit-level time domain simulations. And here we calculate the variation of the current flowing through the squid as a function of the value of the critical current of the nanoclustered magnetic Josephson junction. So with this calculation, we actually observe a curve that has a sigmoid shape. So it shows that this neuromorphic cell with the nanoclustered magnetic Josephson junction can give rise to a sigmoid activation function, which is a very typical shape of activation function that is used in neuromorphic algorithms. Okay, so now that we simulated our neuromorphic cell, we want to validate experimentally our results. So for that, we collaborate with the MIT Lincoln Lab to fabricate this neuromorphic cell. Unfortunately, the MIT Lincoln Lab doesn't have the capability to include a nanoclustered magnetic Josephson junction in the circuit. So what we did instead is that we built 4 identical cells where we replace the nanoclustered magnetic Josephson junction by a normal Josephson junction with a fixed critical current. But for the 4 different circuits, we're going to use 4 different values of critical current. So here is a picture of the circuits when they came out of the foundry. And we can measure this circuit where we measure again the variation of the current flowing through the squid loop as a function of the critical current of the Josephson junction. And what we observe here is that we have a very good match between our experiments and our simulations. So this result is important for us because it tells us that we can trust the numbers that we obtain with our simulations. Okay, so I told you we can also work with a more complex system, where here I show simulation for a neuromorphic cell that has 4 bipolar synapses. So where here, what I mean by bipolar synapse, it means that each synapse has a positive and a negative weight in such a way that it can increase or decrease the current inside the squid loop. So here I show some example of the simulation where we see the output synaptic current of one part of the synapse when we vary only the positive weight. So we see that here's when we vary the positive weight, the output synaptic current varies by about 12 microamp, which translates inside the loop by 0.4 microamp, which is about 3% of this value. So obviously, this number will vary a lot depending on the parameters. But what I wanted to show here is that we can demonstrate the functionality of the bipolar synapse by varying the positive and the negative weight. And in this case, we see that indeed the current flowing through the squid loop would be can be negative or positive depending on the relative positive and negative weight. Okay, so we looked at the functionality of the neuromorphic cell. Now we want to see how we can include it inside a neuromorphic network. So here I show the example where we simulate a high-speed recognition network, which is a 9-pixel classifier, where here we have like our synapses, and here we have our neurons. And the goal of this network is to recognize the letter Z, V, or N out of a 9-pixel image. So for that, we take a 9-pixel image that we decompose into a column vector, which determine if the presynaptic neuron will fire a spike or not. Then we let the system run and do its magic, and we obtain a single spike for the letter Z and no spike for the letter V or N. So which means that the network was able to recognize the letter Z. The network is also robust to a 1 pixel of input noise. So if I take this first pixel and I change it from a 1 to a 0, then we obtain a second spike only for the letter Z, which is the closest from the 3 letters. So by doing that, we can analyze all the images of Z, V, and N with any 1 pixel input noise variation. And we can inject all these images successively in the network, and every time we obtain a single spike for the right letter. So by doing this very simple model, we obtain 100% accuracy of recognition. And we see that our system can run at a pretty high frequency of 125 gigahertz. So here we are aware that this is a very simple network, but we're happy about it because it shows that we can use our neuromorphic cell inside a neural network. So let's see how this nanoclustered magnetic Josephson junction can compare to the performance of other technologies. So on this graph, Nikonov and Young shows like the relative relation of the energy and the delay for different emerging technologies to reproduce the LINET model, which is an example of convolutional neural network. So we want to compare these numbers to our nanoclustered magnetic Josephson junction. So here we're doing some very rough estimation. So we've seen that with our simulations that our circuit with this nanoclustered magnetic Josephson junction can run at a speed of 125 gigahertz, which corresponds to a delay of 8 picoseconds. Additionally, we've measured experimentally that the spiking energy of the device is about 100 zeptojoules. And to do a LINET model, we need about 13 million elements. So these two numbers tell us that for this system, we will need a total energy of 1 picojoule with a nanoclustered magnetic Josephson junction. We also need to take into account the cooling overhead, and that give us a total energy of 1 nanojoule to have the same size of model with nanoclustered magnetic Josephson junction. So if we compare to the other technology, this is where our device should be. So here, I'm fully aware that it is not a fair comparison, since our numbers are obtained with a very small circuit compared to a very big circuit needed for Linet. However, it gives us some encouraging results for a preliminary work, and we still have several decades of space in terms of delay to make it competitive. So before I conclude my talk, I wanted to mention what the next step is for us. So our next step is to move from a simulation to experiment. And so we would like to reproduce the neuromorphic cell and then a neural network at the experimental level. So for that, we design some test structures that include some neuromorphics that allow us to test the neuromorphic synapse functionalities. And we developed a process to integrate the nanoclustered magnetic Josephson junction with the more traditional Josephson junctions, which are used for single flux quantum circuits. So here is the first chip that we obtained. So you can see the picture of the chip inside our cryostat below 80-pin probe card. Unfortunately, our first round of fabrication was unsuccessful. We think that we identified the problem where we had a problem of redeposition during some of the edge, as we can see on this fib picture. So hopefully we identify our problem. We're currently working on having a new run, and we hope to measure to demonstrate the functionality of this of our neuromorphic cell in the near future. With that, I'd like to conclude my talk. So I've shown that the nanoclustered magnetic Josephson junction is a hybrid magnetic and superconducting device, which has synaptic properties. So in this device, the synaptic weight is controlled by varying the critical current with the magnetic order of the device. We have demonstrated that we can build a neuromorphic cell with a nanoclustered magnetic Josephson junction, and that we can include this cell in a neuromorphic network. This work has been done with simulations, and we are now working to the next step, which is to move from simulation to experiments with the integration of where we need to work more on the integration of the nanoclustered magnetic Josephson junction with single flux quantum circuits. And for that, we are still working on the development of the fabrication process. So with that, I thank you for your attention. And before I finish, I'd like to mention that we are still looking for postdocs. And here is a picture of our lab, which is close to the mountain, and we have the chance to be in a beautiful environment. So if you are not scared about trying to work on something new and working with superconducting devices, feel free to contact us. Thank you.
Thank you very much for the interesting talk. And let's thank the speaker by using the reactions buttons. All right, so this talk is open for questions. If you have questions, please raise hand, and I'll call on your name. Maybe I can ask the first question. For the training with the current on the nanomagnetic Josephson junction, the experiment you have done is when you apply a series of current pulses, and it reduces the critical current. Is this training effect reversible? The reason I'm asking is can you rule out that this reduction of the critical current is not due to the damage of the Josephson junction by repeating sending the current pulses?
Yeah, that's a very good question. So I'm going to answer in two parts. The first part is the way we've been doing it lately, mainly because of the way our experiment was set up, is that so we will apply the pulses, we decrease the critical current, and at any time we could actually return, we could always return to this original disordered state. So basically we can repeat the same process. I don't think we are damaging the device. Additionally, we haven't have a good curve yet, so we need to work on our new devices, but we've seen that we should be able to reverse the process by applying pulses. If we can, we hope to be able to apply the right properties of pulse in such a way that we disorder progressively the device, if we do it in absence of magnetic field, to be able to reverse without going back to the initial point. So that's something we're working on. We think we should be able to go both ways, but for now, we always come back to this initial point and just go down, which tells us that we are not damaging the device.
I see. Thank you very much. Do you have other question? By the way, if you're watching this on the Twitch, you can type a question in the chat box and I'll read it for you. I'm sorry, I'm going to butcher your name. Abdel Hamid. Please go ahead with the unmute and ask your question.
Thank you. I want to ask you two questions. So I want to ask about the distance between magnetic nanoparticles, and also the second question, if for your model you told about you use only the magnetic anisotropy, yes? You don't think there is a dipole-dipole interaction. So the dipole-dipole interaction can influence the property of no magnetic just GG junction, and that's mean you can be influence also the critical current. Thank you.
Yeah, those are very good comments actually, and I think you're right. And everything you mentioned is exactly the reason why we want to study, to be able to modify the cluster properties, to study how it influences the properties of the device. So first question was about the distance between our clusters. I don't have the number exactly in mind. I know you can find, I don't have you can find them in this paper right here. So this work has been, the deposition has been done by our colleague at Karlsruhe, and I'm pretty sure we added all these numbers inside this paper. If you don't have it, feel free to contact me and I can go further with you. But what I know is that the numbers that we have highlight exactly the problem that you mentioned. Like right now, we have a pretty high concentration of nanoclusters. They're pretty close to each other, and we are concerned about the clusters interacting with each other. So all of that are valid concern. So yeah, we think the dipole-dipole interaction that you mentioned is probably something happening right now. We think all of that is legit concern, and that's why we want to be able to modify the cluster properties.
Thank you.
Great. Piro, you have a question?
Yes, thank you. Very interesting talk. I just want to clarify what's going on there. So if the magnetic field applied and you drive those current pulses, then the system tends to an ordered state. And if there is no field, it goes to the disordered state. So does it mean that we're just driven towards the stable equilibrium state, or is that not the right way to look at it?
So I'm just trying to clarify. Are you asking what is a mechanism that allows to move to this disorder or disorder state with the electrical pulse?
Well, first the question is it what's going on? Are we driven by those pulses to the equilibrium state? And the mechanism would be the other question, how the pulses help. But is this the right interpretation, that we are driven towards the equilibrium?
So that's kind of the way I see it, in the sense that once I have, if I apply a magnetic field, I am changing the equilibrium state and I'm going in that direction. But it is my interpretation, and I cannot say that it is. As I say, we want to understand better this transport, and I cannot answer before we do more experiments. Some of the experiments we want to do right now would be, well, first reversing the process, as we mentioned earlier. We want to be able to spend more time about studying like the effect of these pulses, like the length of the pulse, the amplitude of the pulse, the frequency of the pulse, how much does it have an effect on all these things. So I think what you said is a correct, it's a reasonable interpretation, but I cannot confirm for sure.
And in terms of the mechanism, I could think of Ørsted fields or some kind of spin transfer torques that depend on the relative orientation. Do you have some intuition of what is likely to be the driving force?
So I am not comfortable using one of these explanations because it will not fit with the symmetries that we see. If we have any Ørsted field, basically, as soon as we change the direction of the field here, we see exactly the same result with this decreasing by the same amount. So I haven't seen any symmetries issues. I haven't seen. Yeah, I haven't seen something that really encouraged me to see that that could be the right answer, but something to explore again.
But I suppose whatever the driving mechanism is, it doesn't have to favor a particular orientation. It just needs to give the nudge to allow the system to jump over the barriers.
Yeah, I see what you mean, but we're also working at very low temperature, which kind of doesn't favor this behavior. So, but I think you have a good point. It's true that in this case, maybe it's about, yeah, as you said, I kind of just getting enough out of equilibrium and not necessarily doing the symmetry. Yeah, it's something I can think about.
Okay, thank you.
I have one more question I want to ask for. I think it's on slide 26. You have an estimation of the overhead of the energy cost from the cooling system. It says 1,000 joule there, but how did you do the scaling to get the total energy to be 10 to the minus 9 joule?
Yeah, I know, because the referee asked us exactly this question, and so the answer, the calculation is described in our last paper. that's one. I do not remember exactly how we went through it, but I can again refer exactly to this paper where I know that we added this calculation.
So
that was a question of the referee. It took us quite some time to answer it in the right way.
I wonder if it's just the volume scaling that even with 10 to the 7 junctions, it doesn't take much of the overall volume.
So here is not, so this cooling overhead we were calculating is not, it doesn't really depend on the number of devices you have, right? We were really calculating how much energy we need to run our cryostat, basically. So we could have more junctions, that would not be a problem.
I see. Dr. Yanko-Milev, please.
Hi, I enjoyed the talk very much. Thank you. If I have to pick here by way of something funny to say, you should keep getting funding until someone finds room temperature superconductivity, and then your overhead is 10 to the third, whatever joules you need for the refrigeration. will push you further away in the good way from the other competitors. Just do it until someone does room temperature superconductivity. But that's not my point. In fact, even not the second is my point. But if you show back slide 13, which we just saw before that, at one point it seemed towards the end that you're able to have speeds like above gigahertz. Now from this plot, I don't see that, but maybe it's a different setting, right? Maybe if you go to lower critical currents, you'll be able to push it even with this thing into the gigahertz. What's the resolution between? How do you get above the gigahertz?
Sorry, are you talking about these numbers that I bring here?
For instance, this one, yeah.
So this one is
parts of a nanosecond is definitely like 10 gigahertz, right?
Yeah, so Josephson junctions have the capability to run very fast. It's been demonstrated to go at several normal Josephson junction have been demonstrated to go, I think, to 300 or 500 gigahertz. So they have ability to run very fast. So this one is only based on simulations. The WR Spice system that we use for simulation take into account all the parameters. So I don't know, here are typical parameters that we use for our materials. And yeah, we can do some time domain simulation. So that's how we get these numbers.
Okay, if I may get to my short
maybe I
question is the following. So obviously this is very exciting because all of a sudden you find a way to look at the Josephson junction like microscopically, so to say, and you begin to play with insulator, which is sandwiched there, and all interesting things happen like we saw. But in my mind, I'm going back to the times when people hoped to make a Josephson junction computer, if you remember these times. And all the point is, can anything be learned from these old advances that are probably well recorded, so that the architecture that was used there or planned to be used could be used now advantageously with this new knowledge when you decide to assemble these things, right? Because
absolutely,
we're most talking about separate elements, right?
No, you're totally right with that. I mean, like, hopefully, like this, a cell like that will be just one part of this circuit, right? So we are interested, and we're looking more at single flux quantum circuits in general, and how we can integrate our junction inside this type of circuits. I can give you an example. God, I forgot his last name. Oh yeah, Graham Rollins, who wrote like a paper on where he does some reservoir computing using Josephson junctions that we could use like this type of SFQ technology to do this type of thing. But the idea would be like we could use our nanoclustered magnetic Josephson junction just to be able to control the output of this reservoir computing, because in this case we need to control on, the advantage of reservoir computing is that you need to modify the weighting only on the outside, on the postsynaptic neurons. So on the output of the network. So like the idea would be like to try to use some of these SFQ circuits that exist already for a long time and see how we could integrate that to this type of technology, which increase even more our motivation to try to develop this process that allows to include the normal Josephson junction and our Josephson junction. I know that I heard someone asked me one day, why don't you do everything? Like in my cell here, I have nanoclustered magnetic Josephson and normal one. And some people ask me, why don't you do everything with nanoclustered magnetic Josephson junction? And one of the answers is because with the properties we have here, our magnetic Josephson are actually slower than what a normal Josephson junction can do. So having a circuit where we can integrate both of them would be a real benefit. And to your comment about like waiting for room temperature superconducting, superconductor. Yeah, first people should work harder on that. And no, but I hear you. But I also think like there are places where we could use this type of application, like any like for example, like when people want to do some fast to use 5G or anything for high frequencies, like all these things you could have at the cell tower level, like you can have a small cryogenics thing. Like of course it's not portable, but there are a lot of places where it is actually not ridiculous to have things working at 4 Kelvin. Right now, I know that in the I don't remember if it was in defense. Like we talked with some people who were explaining that in the defense they have some ways to acquire some very, very small signals at low temperature. The problem is just like they have to extract this signal outside of the low temperature to be able to analyze them. So if we could do some neuromorphic computing directly at low temperature, there is some applications that can be used. Definitely, if you tell me we have a room temperature superconductors, that will make my life easier.
Thank you.
Great. Do we have other question? Looks like there's no urgent question at this moment. Let me remind you that we still have a session afterwards where you can ask questions that's off the recording. So if there's no other question at this moment, let's thank the speaker one more time. Thank you very much. And we'll turn off the recording and the live streaming. And if Emilie, you can still stay for a little bit, there may be some other discussions that, yeah, we can